And now we will have two session speakers talking about system design strategies combining ultra-low power processors and non-volatile memory for IoT, portable, and wearable applications. Our first speaker is Omar Mohammed. Mr. Mohammed is the Technical Marketing Manager of Micronics America. He is responsible for ecosystem, market, products, and business development at Micronics America. His previous roles include business management, project management, product development, and applications engineering. Our second speaker, Eduardo Matanes. Mr. Matanes is the Wearables and Personal Devices Market Edge Processing Business Director of NXP. With over 20 years' experience, Mr. Matanes has focused on IoT edge processors in numerous roles including systems and architecture, business development, and marketing. He is currently responsible for NXP's global market strategy and growth with customers developing trackers, smartwatches, earbuds, headphones, e-readers, AR/VR products, along with other wearables and personal devices. So ladies and gentlemen, now please welcome Mr. Mohammed.
Hi everyone, thank you all for attending. We have a lot of great stuff in store for you today. My name is Omar Mohammed, and I am part of the Technical Marketing Management Organization here at Micronics, a leading supplier in the non-volatile flash memory market. Welcome to our webinar, where we will be talking to you today about ultra-low power design strategies in the battery-operated, wearable, and IoT application spaces. We are excited to have you all here, and to share some insightful information with you all. Today's topics that Eduardo and I will be covering are the following: the growth in the ultra-low power, microcontroller, and non-volatile flash memory markets, key market segments that will be the primary contributors to this growth, why these market segments are driving the push towards lower power, what microcontroller and non-volatile flash memory solution providers are doing to best address this market, and lastly, design strategies that are being implemented to optimize power consumption. Let's jump into it. So, first things first. What exactly is the growth that we are seeing in the ultra-low power space? Why are NXP and Micronics so focused on low power? Well, because on a macro level, we are able to see that there are trends towards lower power. And we can see this from the very first bullet point here. Here we can see that the global ultra-low power microcontroller market space between 2021 and 2026 is expected to experience approximately a 24.8% compounded annual growth rate, also known as CAGR, as reported by Research and Markets. Additionally, we can see that low power will be a key area of focus because while the ultra-low power microcontroller market is expected to experience a 24.8% CAGR between 2021 and 2026, the entire microcontroller market is expected to see only a 10.1% compounded annual growth rate over the same period of time, showing us that the ultra-low power market is growing more than twice as aggressively as the overall market. Lastly, to help us further actualize this information and recognize that this isn't a far-out trend, but rather something that we're starting to see now, is with the fact that in 2020, the ultra-low power microcontroller market accounted for approximately 32% of the total microcontroller market, meaning that already 2 years ago, the ultra-low power microcontroller market accounted for almost 1/3 of the entire market space and units shipped. What these points are showing us is that the ultra-low power space is not only accounting for almost 1/3 of the overall market today, but also that it is growing twice as rapidly as the entire market. Therefore, it is easy to recognize why it should be a key area of focus. So now that we have identified that low power is a key growth area, and an area that both NXP and Macronics are focused on, let me hand it over to Eduardo, who will help us dive in further on specific segments and applications that we expect to see the most growth and shift towards ultra-low power and why. Take it away, Eduardo.
Thank you, Omar. The ultra-low power market is definitely very exciting. As the director of NXP's personal devices and wearables business, I'm very fortunate to be able to work directly with our end customers to see the next-gen trends for battery-powered portable IoT devices. Both NXP and Micronics are critical to the ultra-low power technology that goes into the applications listed here. Let's take a closer look. Let's zoom in on the trends in the wearables market. This is a market that truly excites me as I work directly with many smartwatch manufacturers. The days of 1 day battery life are just not acceptable anymore for us end consumers. So there's a huge push for ultra low power technology to better the battery life. For example, on smartwatches, the expectations are 2+ weeks. For trackers, more than a month. But the challenge is really the increased number of functions that these products need to support. For example, they need to be always connected, BLE to the smartphone, Wi-Fi or LTE for streaming or cloud services, ultra wideband for location or positioning. There's a lot of data being collected by these smart wearables. Smarter sensing is a must with 24-hour health management, a lot of machine learning, but all that needs to do with data privacy in mind. So these devices need to have cryptography to protect that personal data. And the experience from the smartphone is moving into these wearables. So these devices have to have very intuitive user experiences like the smartphone, very vivid graphics, and features like voice UI, voice calling, and audio playback are making their way into these wearables. All these trends are making it more difficult to extend the battery life of these products. So let's talk about how NXP addresses these challenges. NXP's low power technology is your superpower. We have spent numerous years working on battery friendly solutions, not just hardware, but software for wearable designs that are enabling products in the market today to have up to 21-day battery life with functionality like intelligent user experiences, 24-hour health and fitness, voice UI, voice calling, music playback, recording, and we have 15+ wearable products with our end customers globally since the start of 2021. Let's dig into the technology that is driving this low power. NXP wants to be your wearable technology partner. My focus today is going to be primarily on ultra low power processing, but NXP also provides many other technologies that are helpful in developing these battery friendly designs. With low power processing, low power technology, efficient power management, smarter sensing, with cores for machine learning and DSPs for sensor fusion. We also have radios that help these ultra low power devices stay connected. And advanced security is at the DNA of NXP. So we have secure boot, unique key storage, and acceleration of crypto algorithms. And we have GPUs in some of our products to help drive those vivid displays for an intuitive user experience. Let's take a look at some of these components in more detail. NXP's ultra-low power processors are at the heart of these wearable devices. We have both the i.MX RT microcontroller portfolio and the i.MX ultra-low power ULP application processor family. Both of these portfolios are developed in advanced 28 nanometer FDSOI technology, which we'll talk about more in the next few slides. NXP also provides solutions around security, payment, and positioning. As you can see, the devices here listed in bold. We also have connectivity for Wi-Fi, Bluetooth Classic, and BLE. And we have power management with our PMIC with battery charger capabilities and wireless charging as well. We combine our expertise with the expertise of Micronics in their NAND Flash technology to be able to scale in memory, but do it in an energy efficient manner. Let's dig deeper on how NXP's ultra low power processors help extend battery life in these wearable products. It's about the heterogeneous low power computing and really minimizing the area under the curve. All modes, all functions in these devices count. So it's about having the right tool for the job. For example, when the user is interacting with a smartwatch, these devices have multiple cores where the CPU manages one task, the DSP manages another task, and the GPU manages a screen. So by having parallelism of execution, you're able to get the job done very quickly with vivid graphics and move to the next mode. For example, when 24-hour health management, really you need to collect data from sensors and you can process that data later. But having a DSP on board like these devices with the i.MX RT and the i.MX ULP family, you can use that DSP to pre-process some of the sensor data collected while the CPU is power gated and the GPU is power gated as well. So again, you have a lower power profile, you get things done much quicker. And once you get these functions completed quickly, you can spend more time in a deep sleep mode and power gate the majority of the logic and memory in the device. And that's how you achieve the extended battery life in these wearable products. I want to talk about one particular NXP ultra-low power microcontroller, the i.MX RT500 MCU, which has been very successful in the smartwatch market. It's a combination of features in this device that enable the ultra-low power capabilities. For example, the RT500 has an ARM Cortex-M33 that can execute up to 275 megahertz in turbo mode. It's high performance, but it's very energy efficient. We also have a Cadence Tensilica Fusion F1 DSP that allows 13 times better performance for some DSP acceleration. We also have a crypto accelerator as well. We have a 2D GPU that allows rich graphics up to 60 frames per second. And we have numerous flexible display interfaces like MIPI DSI. This device also has very advanced security to keep that sensor data and your own IP and your software protected. The energy efficient DSP included here can also be used for low power wake word and command. And we have a very large on-chip SRAM with 5 megabytes. But the key here is the extendable memory interfaces. In working with Micronics, we have a quad and octal serial interface that can be used to extend the memory to a Macronix serial NOR. This particular device, the RT500, is in many smartwatches in the market today, and it's achieving up to 3 weeks of battery life in smartwatch mode. Let's continue to peel the onion as we talk more about the technology, the processes, and the architecture that the NXP processors include to enable ultra-low power applications. The first topic I want to talk about is heterogeneous domain computing. Like you notice on the RT500, we have multiple cores, whether it's a CPU like the Cortex-M33 or a DSP or a GPU for graphics. So having the right tool for the job allows these applications to execute the function very quickly and spend more time sleeping. We also have created these devices in a 28 nanometer advanced technology, FDSOI, that allows these products to be tuned either for higher performance or lower leakage and do it dynamically with body biasing. All these devices also have dynamic voltage scaling and operation down to 0.7 volts. And NXP continues to push the envelope there, and you'll see products in the future with lower and lower voltage operation. We also have the ability to do state retention of the device down to 0.5 volts. So pushing the envelope when it comes to voltage reduction really helps with the overall energy consumption and the reduction of that for these devices. These devices are all PMIC compatible, so you can use an efficient NXP PMIC to really optimize the power draw from the device, and avoid LDO losses. And last but not least, having very power efficient memories. For example, the Digitimes RT500 has on-chip SRAM, very large on-chip SRAM, with 1 picoamp per bit power consumption. But we also have external memory interfaces, like to the Macronix serial NOR flash, that has caching architecture and buffering. So we minimize the amount of times that we have to go out to the external memory to grab a line of code, in order to, again, reduce the power consumption of going to that external memory. Even though those memories, obviously from what you're hearing from Omar's presentation, are getting much, much better in operating at much lower voltages as well, helping the overall system power consumption. So far, we've talked a lot about hardware, technology, architecture, processes that help optimize the battery power consumption. But it's also about the software support. NXP provides several wearable software packs to help enable many of the functions in these devices that I've described. It's not just about looking at the microamps or megahertz specs from a particular microcontroller or application processor. It's about the power consumption of a particular use case. So NXP has spent time focusing on real use cases and the applicability of these use cases on our devices. So for example, here is the average power consumption of different use cases in these wearable devices on the i.MX RT500. So we have software technology, some that is complementary and some that is premium offerings for voice assistants, for example, VIT, that can do wake word and command and control in these end products, leveraging the on-chip DSP, and do it very efficiently. As you can see here, approximately 2 milliwatts for a voice assistant. We also have software technology like Conversa to enable voice calling at about 11 milliwatts. We've also enabled a DSP with several codecs to do music playback, like this MP3 example here at 4 milliwatts, and even record MP3 files from your own voice on these wearables with 4.6 milliwatt average power consumption. We're working on increasing the number of use cases in these software packs that we support, either through NXP technology or also working with partners to develop things like health sensing, voice calling through radios like BLE and LTE, and music streaming applications as well. So overall, you've heard from me about NXP technology that can help enable lower power consumption in your end product. I'm going to turn it over to Omar now, who's going to jump in to the Micronics technology that is also helping these applications. Thank you.
Thanks, Eduardo. Wow, it is great to see all the exciting things that NXP is doing in this space to support low power applications. Similarly, we at Micronics also realize how important it is to support ultra-low power. And so, because of that, we have done a few things to help system designers to reduce their overall power budget. This slide, which I will go into more detail on shortly, highlights what we are doing on the hardware design side that is catered towards battery-operated applications, as well as applications requiring low VCCN. And on the other side, we have implemented power management features baked into our non-volatile flash memory to help the system optimize overall power consumption, which I will touch on more on a later slide. Now, going back to this slide, as I was mentioning, on the hardware side, we have taken a great deal of effort to design and develop our 1.2 volt solution. I would also like to add that we at Micronics are are the first non-volatile flash memory supplier to take our 1.2 volt serial NOR flash solution to mass production. So, why did we place such a high priority on developing and releasing a 1.2 volt solution? Well, because we see that process nodes continue to shrink in the microcontroller space. And while they continue to get smaller, the expectation is to consume less power and operate faster with every generational iteration. So, in order to support this technological shift, I/O and core voltages are decreasing from 1.8 volts down to 1.2 volts. The goal behind this effort to lowering core and I/O voltages is that with this reduction, the expectation is that overall power consumption will also go down, since, as we know, power equals current times voltage. Now, let us take our attention over to the image on the right. Here, what we are highlighting to you is that as the microcontroller shifts to 1.2 volts, it benefits the overall system for the peripheral components to match this voltage because, on one hand, the system is able to conserve power when the peripheral components' input voltages match the MCU, because the system no longer requires additional components such as low dropout regulators, also known as LDOs, voltage regulators, or other forms of boost circuitry, which by design are impossible to be 100% efficient. Additionally, by eliminating these extra components, there are also several other advantages as well, such as a reduction in complexity in the overall design, more room in the power budget, a simpler circuit board layout, and a lower bill of materials. Not only will a system architect's design become easier to maintain, but by eliminating these additional components, the device will be able to last longer in the field, shrink the overall solution size, and ultimately cost less to produce. Next, let's take a look at a practical application example. Alright, so here is an example of a wearable application that leverages IoT sensors and operates on a finite power source, i.e. a battery in this case. This device is called a continuous glucose monitor, or CGM for short. A CGM is a wearable medical device that automatically tracks blood sugar levels continuously throughout the entire time the user wears the device. The way this works typically is that there is a tiny sensor that is inserted under the skin, which measures interstitial glucose levels, which is the glucose found in the fluid between the cells. The sensor tests glucose every few minutes. Then, a transmitter wirelessly sends this information to a separate device, such as a smartphone or tablet, or in some cases, an insulin pump. For those who are unfamiliar with what an insulin pump is, it is a device that is used for insulin delivery to help regulate glucose levels. What makes this device such a great example is that as a device that continuously is monitoring glucose levels, it needs to be able to operate in the field for long periods of time between charges, while being able to operate solely on a wireless type power source such as a battery. As well, it needs to have some sort of connectivity so that it can not only collect data from the user, but also be able to send that data out somewhere else so that it can be further processed and analyzed to help provide something meaningful back to the user. And of course, since this is a wearable type application, a CGM needs to be small in size and form factor, otherwise it will be too cumbersome for someone to wear it for days at a time while living out their everyday lives. And lastly, as most devices in this space, they are manufactured in large quantities, and therefore, before they are in the hands of the end customer, they are on the shelf for long periods of time. So because of that, CGM devices must have little to no leakage current to prevent battery degradation. Hence, for a continuous glucose monitoring type device, these design features listed here help to illustrate perfectly the challenges system architects face when developing these types of solutions, as I highlighted earlier. The ability to operate for long periods at a time on a single charge, the need to keep the physical dimensions small and lightweight, the flexibility to reside on a shelf for a period of time with little to no power leakage before an end customer purchases it and starts to use it, and the ability to collect, store, and transmit data while still maximizing overall power consumption. So now that we've identified some of the design challenges CGMs face, let's look at some non-volatile flash memory design strategies CGM architects have at their disposal to help them. Alright, now that we have addressed and aligned on the challenges that continuous glucose monitors face, let us now discuss how we at Micronics are focusing and working to address and mitigate these design challenges to make life easier for system architects. As I showcased in an earlier slide, when discussing 1.2 volts, we at Micronics have developed and taken to mass production our MX25S solution, which is our 1.2 volt solution. The benefits of the MX25S that support a continuous glucose monitoring application is that first and foremost, the fact that it can operate at a really low input voltage. And as we have discussed in the earlier parts of this webinar, we know that power equals current times voltage, and that the overall trend is that there is a growth in the ultra-low power space, and that the majority of that growth is in mobile applications using battery as the sole power source. Therefore, anyone looking to increase their overall power efficiency or reduce their overall power budget will look to solutions that have lower VCC requirements, the CGM being one of them. Therefore, the MX25S is a perfect fit. In addition to the low input voltage, to help address the first design challenge, which is the ability to last a long time on a single charge, we also are able to address the challenge of helping to keep the end solution small and lightweight by offering a multitude of package offerings. Here are some of the smallest among them, which are 8 USON, very, very thin, small outline, no lead package, WL CSP, wafer level chip scale package, and KGD, known good die. This isn't necessarily exclusive to our MX25S solution, as a vast majority of our solutions offer different package options to fit any design needs, but it is a great feature to highlight in the CGM example because, again, the need for a small and lightweight overall solution is very important for a CGM type application. As well, to help address the third piece, which is the need for a long shelf life, i.e. the challenge to have little to no power leakage before an end customer has had a chance to start using the device, the MX25S helps to mitigate this challenge by offering an ultra-low power down option where the current consumption is only 50 nanoamps. Now, when the unit is in use and the device is operational in a typical use case condition of periodically waking up, collecting information, then sending that information out to a third-party device for further processing, and then going back to sleep, we need to be able to quickly perform that wake-up and sleep mode operations. But as well, we need to be able to have that mean something when it comes to power consumption and overall power management, i.e., it wouldn't make sense if the microcontroller tells the memory device to go to sleep and the memory device continues to consume the same amount of power throughout this entire dead time, because it would only just drain the battery unnecessarily and prevent the system to perform other necessary resources, as well as limit the capabilities of the CGM device to be able to add more possible features because that power is being taken up by the memory. For this reason, we at Micronics have implemented power management capabilities, such as a bit that the microcontroller can send to the memory to let us know that the memory is not actively needed. And with this, we can then switch from a high performance mode to an ultra low power mode. And the benefit here is that with these modes, we can turn on, quickly do what the microcontroller needs from us, then as soon as the operations are completed, the microcontroller can just as quickly tell us to go back to a state where we consume very little power to free up those resources for other parts of the system. Now, as we know, a continuous glucose monitor isn't the only type of wearable application leveraging IoT and using a finite power source such as a battery in the market today. So, let us take a look at another application. In this example, we're looking at a smartwatch. To review, a smartwatch is a portable device that is worn on the wrist and offers an almost endless supply of features. Some offer the ability to track aspects of your health, such as the number of steps you have taken in a day, or your heart rate, or even the ability to track blood oxygen levels. And some offer the ability to act as your smartphone, i.e. the ability to make or receive phone calls, read and answer emails or text messages, or even keep track of your calendar. Now, as you can see here in this slide, not much is different in terms of the design challenges that smartwatch makers face. Therefore, we can see some overlapping commonalities that the overall wearable IoT markets are experiencing, i.e., once again, the fact that these devices need the ability to operate on a single charge for a long period of time, because similar to a CGM, a smartwatch wouldn't really capture much broad market adoption if users had to go back and charge their devices every few hours. As well, smartwatches are also devices that need to be small and lightweight, which means that similar to CGM architects, the components that smartwatch architects select need to also be small because of the very little real estate that is available to them. And of course, the ability to have a long shelf life until an end consumer is able to purchase the unit and start using it. As mentioned earlier, unlike a CGM device, a smartwatch has the capabilities to perform a lot of different tasks and collect and monitor a lot more information. However, if we break things down, the need from a non-volatile flash memory supplier are not all that different. Essentially, what is required? A smartwatch ultimately is collecting data periodically and then transmitting that data to a third-party device, which is typically a smartphone, and then between active states is working to use as little power as possible. So, from our perspective, a smartwatch is not all that different than a continuous glucose monitor. It is like other wearable applications leveraging IoT and is using a battery as the sole power source. However, with that being said, we recognize that the way end system designers may go about architecting their solutions may be different and therefore require a different type of solution. Which is why we at Micronics also offer more than just the MX25S series to support this market segment. Here in this example, we showcase our MX25R family of products, which are all already in mass production. We have a fairly wide density range from 2 megabits to 64 megabits to fit every kind of application need. The MX25R product line is great for any application that has not yet shifted towards a 1.2 volt VCCN, as the input voltage range is between 1.65 volts to 3.6 volts, i.e., it is a great product for solutions that need a device with 1.8 volt VCCN or 3 volt VCCN. The MX25R family is able to address the design challenges for a smartwatch because it has similar package offerings to the MX25S, which is, once again, the 8 USON, very thin, small outline, no lead package, WLCSP, wafer level chip scale package, and KGD, known good die. To provide a bit more color to why this is important to highlight is that if we were to compare a 8 SOP package solution, which is around 41 millimeters squared, to our WLCSP or KGD package solution, which is 3.1 millimeters squared, we can see a huge savings in size, approximately 92% in size reduction. And as we discussed earlier, we know that for devices like CGMs or smartwatches, how critical overall solution size is and how important it is for each component to be as small as possible. As well, to help address the third piece, which is the need for a long shelf life, i.e. the challenge to have little to no power leakage before an end customer has had a chance to start using the device, the MX25R helps to mitigate this design challenge by offering an ultra-low deep power down option where the current consumption is only 7 nanoamps. This device uses almost no power when in deep power down state. So, unlike a CGM device that spends more time continuously reading and transmitting data, for a smartwatch type of application, the MX25R is a great solution fit because of its ability to have similar power management capabilities to the MX25S, i.e. the ability to quickly go between a high performance mode and an ultra low power down mode, but with an even lower deep power down state of 7 nanoamps. This helps to maximize power throughput out of the battery, especially during times where the memory is not in active use. Alright, so you might be thinking, since the MX25S and MX25R both seem to fit the IoT, wearables, and battery-operated application spaces, then what exactly is the difference? Well, here we highlight both products and compare them side by side along with our standard 1.8 volt MX25U product line. You can see here that both the MX25S and 25R parts offer the ability for a high performance mode and an ultra low power mode. MX25S has a voltage range of 1.14 volts to 1.6 volts. Therefore, it is more suited for applications requiring 1.2 volt VCCN. While the MX25R has a wide range VCCN from 1.65 volts to 3.6 volts. Therefore, it can support applications that leverage 1.8 volt VCCN or 3 volt VCCN. With respect to deep power down current, we can see that MX25S matches the 1.8 volt part at 50 nanoamps, while as the MX25R goes as low as 7 nanoamps, as mentioned earlier in this presentation. However, the read frequency is much faster on the MX25S at 120 MHz for both high performance mode and ultra low power mode, while the MX25R is 80 MHz during high performance mode and 8 MHz for ultra low power mode. Now, looking at things from a power consumption perspective, let us compare the MX25S and MX25R to MX25U, which we use as the baseline. So how we want to look at this slide is as a percentage. As I mentioned, we use the MX25U as the baseline value, and from there measured how the MX25S and MX25R perform with respect to the MX25U. Therefore, as you look at this slide and see 0.4x, that means that the MX25S device for this I/O read operation, the power consumption is 40% of the MX25U, meaning that about 60% less than the MX25U. So, just to call out to a few highlights here, when going through this table, we can see that, again, going back to the read operation, the MX25S is 40% that of the MX25U, while as the MX25R is 98% that of the MX25U. So for read operations, you can see that the MX25R has a 2% savings when it comes to power consumption, and the MX25S has a 60% power savings when compared to the MX25U. And another function is block erase. The MX25S is 30% that of the MX25U, while the MX25R is 56% that of the MX25U when in high performance mode. Of course, if you are interested and need additional information on these products, feel free to reach out to us and we can help you pick the right solution for your application. Wonderful! I know we have covered a lot today, and I would like to thank everyone for joining today's webinar. Before we conclude today's session, I would like to reiterate a few key takeaways. We know that the ultra-low power market is not only on the rise, but is also expected to outpace the overall market. We determined this in the beginning when we discussed that the ultra-low power market is expected to grow approximately 24.8%, while the overall market is expected to grow only 10.1%. A key contributor to this growth will be thanks to the increased adoption of IoT sensors with their ability to collect more data than ever, as well as the requirement for devices to last longer and longer in the field between charges. With these additional features and components comes the added complexity of how will a system architect be able to manage the overall power consumption of their device? Well, we hope you were able to take away that both NXP and Micronics are here to help and support you in this new market landscape with the material that we've shared with you today, such as NXP's I.MX RT and ULP family, and Micronics' 1.2 volt and wide range VCC solutions. If you are interested in learning more, you can feel free to use the QR codes here at the bottom of the slide for both NXP and Micronics that will take you to our respective additional resources. I would like to thank Eduardo for being my co-host today, and thank you all once again for attending.